The primary reason all large celestial bodies like stars, planets, and moons rotate on their axis is the law of conservation of angular momentum. This fundamental principle of physics, combined with the process of gravitational collapse, dictates that any celestial body formed from a swirling cloud of gas and dust must spin. The origin of rotation. Initial molecular cloud. The process begins with a vast, cold, and turbulent cloud of interstellar gas and dust. This cloud is not perfectly static. It has tiny, random movements caused by events like shockwaves from a nearby supernova. This gives the cloud an initial small net angular momentum. Gravitational collapse. Due to its own immense gravity, parts of this nebula begin to collapse inward. This gravitational collapse is the key driver of the formation of a new solar system. Conservation of angular momentum. As the cloud collapses, its size dramatically decreases. To conserve its total angular momentum, its rate of rotation must increase. This is the same effect that causes a figure skater to spin faster when they pull their arms inward. Formation of a spinning disk. As the cloud shrinks and its rotation accelerates, it naturally flattens into a spinning protoplanetary disk. The central part of this disk becomes the star, while the planets and moons form from the remaining material in the disk. Perpetual spin in a vacuum. Once the planets and moons have formed and swept up most of the surrounding debris, they are in the near vacuum of space. With virtually no external forces to slow them down, they continue spinning due to their inertia, much like a rolling ball on a frictionless surface would never stop. Mathematical explanation. Conservation of angular momentum. The principle of conservation of angular momentum states that for a closed system, the total angular momentum, L, is constant. The angular momentum, L, of an object is defined as L equals sine I omega, where L is the angular momentum, I is the moment of inertia, a measure of an object's resistance to changes in its rotation. For a simple point mass, ImR2 omega is the angular velocity, which is the rate of rotation. For a collapsing cloud of mass, m, the mass remains constant. The average radius r decreases dramatically as it collapses. The moment of inertia, I, is proportional to r2, so as r gets smaller, I also get smaller. Because the product IO must be conserved, if the moment of inertia, I, decreases, the angular velocity, omega, must increase. L underscore initial equals sign, L underscore final I initial I final O final. Since I finally initial, due to gravitational collapse, it follows that O finalo initial. This mathematically demonstrates why the initial slow spin of a nebula is amplified into the rapid rotation of a star or planet. Example: the Sun and the protoplanetary disk. A young massive star like our Sun forms from the center of the nebula. As the nebula collapses, most of the mass goes into the Sun, but the majority of the system's angular momentum is transferred to the orbiting protoplanetary disk. This explains why the Sun spins much slower than would be expected given its mass, while the planets contain the bulk of the solar system's rotational momentum. Modifying factors and variations. While the conservation of angular momentum explains the origin of spin, other factors can influence the final rotational properties of a celestial body. Collisions. Impact events with large objects can significantly alter a planet or moon's rotation. Uranus's axial tilt of nearly 98 degrees is thought to be the result of a large collision early in its history. Similarly, a massive impact on the early Earth is the leading hypothesis for the formation of the Moon. Tidal locking. For moons and planets in close orbits, tidal forces can slow a body's rotation over billions of years. This gravitational interaction transfers angular momentum between the two bodies. A tidally locked body, like our Moon, has its rotation period slowed until it matches its orbital period, always showing the same face to its partner. The transfer of angular momentum from Earth's rotation to the Moon's orbit is also causing our day to lengthen by a few milliseconds per century and the Moon to slowly recede from us.